Hi there. Today I am going to be covering a few topics in our artist masterclass for everyone in world. I am sitting in there just to answer questions and go along, but today is going to be a bit more of a sidetracked art class because I really want to teach some of the more advanced features that we've got available in space, starting with shaders. So, I think probably the best thing to start with is just a quick overview of what a shader is, and then we're going to get into the nitty-gritty of actually how you can start authoring your own shaders. Now, this is a bit of a technical topic, but I think that the results do speak for themselves. This is a topic that programmers will have a little bit of easier time with than artists to begin with, but there are tools available which I'll discuss shortly on how to author shaders in a bit more of a artistic and procedural manner rather than having to do it by hand, which is what I'll be teaching today. There are other topics I want to cover today. Specifically, I want to get into, if I can, depending on time, I want to get into particle systems, volumetrics, animation, and potentially a few other nifty little bits and pieces, but I suspect that at least getting into the start of shaders today is going to take up quite a lot of the time. So, welcome. If you haven't watched these before, I'm going to speak for the next hour showing off various parts of Unity and how they work with the Space Virtual World platform, and hopefully that you learn something. I'm sure that today you will, because this is really the single area where you can go from good-looking content to really impressive, amazing-looking content. Now, I do apologise. I have lost my notes for this this talk today due to a power outage about 5 minutes ago. However, I will be should be able to do this all off memory just fine. Okay, so first things first. What is a shader? A shader is a small program that runs on your graphics card, telling the graphics card how something should appear on screen. That is the short of it. Basically, it's a little bit of code that indicates exactly how something is drawn. So whenever a object is rendered on the screen, it will be rendered according to the instructions that it receives in the shader. So it might take the input data, such as the meshes, the textures, that kind of thing. It'll run its program, and then the output will be a single color pixel, which is sort of how the object is rendered. Shaders are at a very low level, and they give you a tremendous amount of power in terms of how you want things to appear. Generally speaking, you are often using the Unity standard shaders that are built in 99% of the time. For objects that need to render realistically, the realistic shaders that come with Unity, such as the standard shader, are more than you will ever need. However, today we're going to discuss a topic of non-photorealistic rendering, and we're going to look at doing some nifty tricks with shaders, specifically how to basically make things look unique, interesting, and varied in a way that is going to make your scene pop. So today I'm opening back up with the Savannah scene that we've been testing for the last couple of weeks. This one I'm just going to use as a demonstration because it's got a bunch of objects in here already. But what we're going to do is we're actually going to make this scene look non-photorealistic, and we're going to start by building a shader that covers sort of holographic effects, because I think it's a nifty way of getting started into shaders, and then we can actually look at things like warping the models. Finally, we can get into whatever we wish. If you are in World and you do have particular ideas for how you'd like this shader to look, I will at least skim in World chat while I'm talking today, and hopefully there's something useful you can learn out of it. So, to start with, when you are building in Unity, every object has a material attached to it. And if we go here to the material on the sidebar, you can see here that there is a shader selected. So 90% of the time you're using just this standard shader, but you can use custom shaders. So, what does a custom shader look like? I'm going to pull up a new folder here. We're just going to call this one Masterclass, just so I'm not lost. Okay, and you go right-click, Create Shader. Now you've got a couple of options here. For today, we're going to be only concerning ourselves with the standard surface shader, because that gives us a lot of the boilerplate that we need for building shaders and takes away 90% of the work that you need to do when authoring one. However, the unlit shader gives you a greater amount of power in terms of the template, but you have to write a lot more code to use that. The standard surface, so when you're building shaders, a shader is a combination of a couple of different little programs. So you've got a program that renders the fragment, and that is basically what the pixel is rendered as. So 90% of the work that you're doing will again go into the fragment shader. You also have a vertex shader, which lets you modify and update vertex information on the fly. And there is also room for potentially things like tessellation shaders and things, and compute shaders and other kinds of shaders that can go in here. But for today, we're really only going to be concerned with fragment and vertex shaders, and the standard shader, the standard surface shader that Unity provides as a template when you're creating a new shader. That standard shader gives you a vertex and a fragment shader straight away, and it gives you a sort of a one that renders to realistic lighting. So if I start from here, I'm going to create a new standard surface shader. I'm going to call this Savannah shader. And this is going to be the shader we're going to apply to one of these objects. So I'm just going to grab one at random. Perhaps we'll play with a couple of these in a second, actually. So I might just grab this tree. This is going to be our shader test today. So what I'm going to do is, first things first, I'm going to copy the material that's on here and just apply our shader to it. So it looks like this may be a combination of two materials. No, it's just one. And you can see here that it's just got an albedo and a normal map currently, and a couple of things for metallic and smoothness. Now, one thing to note is that this shader is actually written as a cutout shader. So most shaders, there's a selection of choices you've got when you've got to how a shader renders intrinsically when you're doing a surface shader, and you can pick between things like transparent shaders or solid shaders, and that determines when the shader is run. So in Unity's renderer in particular, there is an order to the way objects are rendered. The first things are rendered are the solid objects, that's got no transparency in it. Then the next thing it renders is objects with cutout. So if you're using alpha cutout like here, you can see that this is a solid object that sort of changes a bit, and it cuts out the shader based on the alpha value. Finally, you've also got actual transparency, which you can see is slightly smoother on the edges when you use transparency. Nonetheless, for today, we're going to be dealing with just what this is, and this is a cutout shader. So we'll need to look up some things during the course of writing this shader to make sure that it actually matches. The simpler ones are the opaque, which are the defaults. Because the order of things rendering, it actually means that if you're doing things like shaders that manipulate the background of objects behind them, it can have some impacts in how that goes. But for today, we're going to keep it simple, and we're going to go for the basics of a shader. So I've created a new shader. I'm just going to duplicate this material. So I'm not modifying the original assets. So just duplicated that one, and this is going to be Savannah tree shader. We're just going to swap this onto here. So now this is running on its own material, which means that it won't modify anything else in the scene. So I'm just going to grab the new shader we made. So when we made it before, you'll see it'll show up here under custom by default. We can change the names of this stuff pretty easily, but for starters, it's custom Savannah shader. Now you can see this is running our custom shader. And as I mentioned before, because the default is for opaque, we've now lost our alpha cutout. So what I'm going to do is I'm going to go edit shader. I'm just going to bring up Visual Studio. For me, if you're using a different operating system, you'll get different requirements. So the first thing we've got to do is we're going to make this an alpha cutout shader, just so we can get back to where Unity was as far as the standard shader. So when you look at a shader here, there's a couple of blocks. First, you've got the shader block, which you can see from here to here. Now, I apologize for non-programmers here. This is going to look absolutely scary. It's not that bad, but that definitely does help if you've got some programming knowledge. If you don't have any programming knowledge, don't want to learn any, and this is confusing, if you come back in about half an hour or so, I'll be moving on to the next set of topics. But for today, we are actually going to get deep into a little bit of code here to show how to do it. Now, there are some alternatives to writing these by hand. There is at least 2 assets on the Unity Asset Store that provide visual node-based editors, similar to that's available in Unreal Engine. There is Shader Forge, and there is another one which has a similar name, which is escaping me from the top of my head. Both of those assets let you use a node-based designer to build your shaders, but for today we're going to be doing it the manual the manual way in doing it in code. And I'll go through and I'll try and explain actually what these blocks are, so you may be able to learn and mess around on these. When I first started programming shaders, I actually didn't start programming shaders until quite late, actually, probably not until 2012, 2013. I actually learned them because I looked at this as coming from a programmer and thinking, this is so alien, I'm never going to learn this, I won't bother. I really shouldn't have, because frankly shaders are probably one of the easiest sets of programs that you can write, because they are very, very, very tolerant of you making mistakes. And this is not necessarily a good thing. And the other thing is that they're actually a lot simpler than they look, and especially with Unity's surface shaders, they take care of 90% of the work that you need to write. So this whole shader that's rendering accurate, physically based objects is only 50 lines of programming code, of which about half are white space and comments. So really it's only about 20 lines in total. So today we're going to start by going through these. So the first thing is the shader block. So this block here, which covers the whole shader, basically indicates that this is one grouped shader. And you can see it's got a name attached to it. So if I name this something else, you can actually see how that affects in Unity. So I'm just going to call this Atom, and I'm going to make Savannah shader a bit nicer there. So now when I tab back to Unity, Unity will recompile it, done, and you'll see now that the shader is actually listed under the Atom Savannah shader there. So you can actually organize and group your shaders just by changing the name there. Very straightforward, very simple. Next thing we've got here is the property block. Now this isn't actually programming code. This is just a set of indicators to Unity of what to display on the sidebar here. So if we look here, we've got color, main texture, glossiness, and metallic. And here we go on here, we've got color, main texture, glossiness, and metallic. They have the name is there inside the property block. Here is the type, so that's how it should be presented. And then over here is the default values that show up. Generally speaking, you'll be cutting and pasting most of these most of the time. So to get our thing back, we also had a normal maps texture. I'm just going to add a second texture block for the normal. Now I'm naming this one bump map. There is conventions to how these things are named. You don't have to name them in any particular way, but if you name them the same as the standard conventions, it will save you a bit of hassle because Unity will automatically keep those shader values when you swap between the different shaders. It'll automatically populate them with the textures that were previously set, whereas if you've got unique names on everything that only come to your shaders, when you swap into your material, you'll have to refill out all the properties. So this one's just going to be the normal map, and now when we go here, you'll see that we've got the normal map back, and that's the one that we had in here before. Now the second thing is when we added a property, that's only changing it here on the sidebar. It doesn't actually add it to the shader itself. So the next thing we want to do is we just want to add a variable which has got the same name in here, which will be the one that's actually passed to the shader. So the type of the thing here is a sampler 2D, and that just means it's a texture. So in this case, we've just got bump map. And now when we pump back into here, it should still compile, or maybe not. Oops, because I typoed. It should be sampler, not sampled. There we go, and now this has got the bump map. Now it doesn't actually have it implemented yet because we need to write some code to tell Unity that we want to grab the bump map. So the first thing we want to do is add here this to float UV the input. Now this is the stuff that Unity will pass into every shader, sort of setting it up. In this case, we want to just pump the UV data for the bump map. Now this is the UV coordinates that sort of determine how textures are rendered on the mesh. So I just added that one for the bump map, and that handles things like the scaling and the offset and things on the textures. Now to actually implement it, it's a fairly straightforward process. You will need to sort of pick up and learn a few of these things on your sort of own, but the Unity documentation on shader authoring is pretty good. So we're just going to grab the color value of the normal map here. So I'm going to call this bump, and actually I'll call it bump, and I'll just grab the texture. I'm just going to grab the bump map texture, which is defined up here, and I'm just going to grab the UV coordinates from here and put it there, and you can see that the in is actually passed in on the first variable of the surface shader there, and that's actually just a copy of this input structure that Unity has filled out. Now, Unity determines what they are by the naming, so there is a naming convention that you need to use here. For instance, if we want to grab the world position of a shader, the XYZ coordinates, we can do that by actually using a float3 world pos, and Unity will recognize that that's the world position and pass it in when you want to use it. We will actually use that one in a minute. But first things first, let's just get this set up to the same as it was before. So this one, it's a bump map. Now, this is not going to work, but I'm just going to put it here. First thing, so if we go o.normal, and that's the output, which you can see here is the standard output. There's a array of these declarations. There is the normal, the albedo, which is the sort of the diffuse texture, the metallic, the smoothness. We've also got emission, and there's one or two others that are sort of hidden and out there. And these are the output variables that Unity will use for determining how it should render through the normal lighting pipeline. If you don't want to use the Unity surface shaders and write your own lighting pipeline, you can. There is quite a bit of power available here, but to begin with, we're just going to put this one in. So we go normal equals bump, and what's going to happen here is this is going to look really weird if it works at all. Not too bad, but that's not actually showing the bump map correctly. To use bump maps, you actually have to use something called unpack normal. So you just use unpack, and that'll depack the values of how the normal map works. I'll just set that to a half 4 as well, versus a fixed 4. We'll go into that as well in a second, but for now, I think maybe it should be half 3. There we go. So now this has actually got the bump map applied correctly. Probably can't really see that, but if we put the point light on here, it might be a bit more obvious. So now we've just got a standard shader that sort of matches. The only thing we're missing is the cutout. Now, cutout in Unity is handled with something called an alpha test variable. And I'm just going to quickly, because I did lose my notes here thanks to that power outage, I'm just going to quickly grab the reference docs on exactly what the standards are. So, for reference, if you use Google and you search for Google Surface, Unity 3D Surface Shader examples, there is a there's a fantastic documentation page in the Unity manual which actually covers sort of some simple examples of how surface shaders can be used. So in this case today, we are going to use I don't know if they've actually got the thing in here. Oh, the other thing is worth noting is that Unity built-in shaders can actually be downloaded. So if you go to Unity built-in shaders, we can see here that in the download archive for Unity, we can grab some. So what I might do is actually, I'm going to go copy Unity's default shader here a little bit, just a couple of lines of it to get the details I need here, because I don't know this one off by heart. Okay, so we're just going to go in here and grab the one that we're looking for. It's called alpha test, and that means cut out. So I'm just going to grab the alpha test diffuse and take a look at this one. I can't just view it. It's annoying. You'll do. Just 1 second. Okay, right. So here you can see this one's also quite simple. So the first things we've got here is we've got a set of different tags. Now when a shader is written, these are not part of the program, but Unity uses them to determine what kind of shader it is. So I'll actually quickly explain all of these tags. They're just a set of keys and values which indicate sort of how the texture should render. So the first thing is the Q. Now the Q in Unity parlance basically is when the shader is rendered. So in this case, they render opaque first, then they render alpha tested stuff, then they render transparency stuff, and then finally they render what's called overlay textures, which might be things like the user interface. So in this case, we want to put it in the alpha test queue because it is an alpha tested surface. If we put it in an earlier queue, we might end up with holes in our material because of the way that depth sorting happens. The next one we got here is ignore projector. This is basically tells Unity to ignore this shader when doing things with the built-in projector system. We don't use the projector system much, no one really uses it, so this line is somewhat optional, that there's very few cases where the projectors are actually in use. But if it is in use, it saves a bit of performance time because the projectors are quite laggy. They require re-rendering the whole scene a few times in order to pull their effect. The next one is the render type, and this tags the shader as a transparent cutout, and this basically is used by a bunch of visual effects potentially later on, which may replace shaders. It knows what to replace it with, what kind of category it is in. These last two are optional. The Q is somewhat mandatory. If you don't include one, it'll default to the opaque Q, but you should always be specifying one of these. The next thing we've got here is work alpha test. So this is this basically tells Unity that its surface shader should implement all the code for alpha testing, which is the cutout. Alpha test meaning that if it's lower than a certain particular cutoff value, it should go away. Now to implement this, we do need to add another variable to our thing that just is called cutoff. This is again something that you just need to memorize and commit to memory. This is not anything sort of innovative, it's just a simple recitation. So I'm just going to put cutoff here, and I'm going to put alpha cutoff, and it's just going to be 0 to 5, and that's fine. You don't need to declare, for this particular variable, you don't need to declare it in here because Unity actually declares it for you when you specify this. So now if we go back into our scene, you see we've got our shader back. So this now should be identical to this. They both should look the same because they're both doing the same thing. I'll just remove the light and you can see that, yeah, they're rendering the same. So this is now rendering on a custom shader, which is implementing 99% of the same stuff that the standard shader is. The only difference is that the standard shader's got a lot more options, and basically what we've done is we just need to do the same thing that we did for the bump map. We just need to repeat that process for all the other slots if we want to actually implement them. So we've got our basic shader. Now we're going to do something interesting. We're going to say, I think I said we're going to turn this into a hologram. So first thing we might want to do is change the lighting model. Now the default lighting model is just render it as normal. But what we can do is we can actually set a blend mode on this. And if we set a blend mode, it's kind of like Photoshop's blend modes. In this case, we'll just use the add. So this is the equivalent of the screen blend mode in Photoshop. So if I just type decal add, this is again one that you just need to memorize. There is a big list of these on the surface shader page. So we've lost our alpha cutoff, but this should now should be just brightening up the stuff behind it. In this case, it is not. And this might cause... Oh, I might need to switch this to emission too. 1 second. I'm just going to set this to O.L. Whoops. Float 3000. And this is how you can declare arrays. Just you can type them as that data structure. So I'm just going to set this one to emission. Hopefully, it's going to do what we want. I'm not 100% sure it is, so we'll just duplicate this a couple of times. Yes, I'm not sure this one is rendering the way we want. Decal add got a couple of changes. I think we might need to keep it off. This would be annoying if this is misbehaving. This is just my luck. I did actually have a sample a minute ago. Okay, so I might take this one off and we can use blend perhaps. 1 sec. This is where looking up the manual is a good idea. So I'm just going to grab from... Oh, did that actually work? Oh yes, okay, so we've got that worked. There we go. So in this case, we've now got the object, so it's actually brightening up the area around it, you can see. So what we've done here is we've actually used a Unity blend mode. So if we go Unity 3D blend shader blend modes, you'll actually see all the keywords that are available. There's quite a few of them. So in this case, you can define almost any blend mode that can be produced by Photoshop's own blend layers using this stuff. So in this case, we've now got our tree is actually bright. So if we lower the scene lighting values, so I'm just going to set the environment lighting right down. And I'm going to clear out our baked data if we've got any. We don't. Okay, where's our directional light? I'm going to make this a nighttime scene effectively, so I'm just going to pull this into blues and lower that down. Now you notice that this tree is actually, it's emitting light. It's not actually part of the scene itself. And what we did a second ago with the emission values was actually switch how lighting works. So when we first talked about lighting back in the first masterclass, I mentioned that lighting comes from a combination of factors. It comes from the base environment lighting, actual lights, so the environment, then the lights, then probes, then reflections, and a few other things. One of the last ones is actually emission. So each object can emit light on its own. Now if you use it in the standard shader with the emission checkbox, it'll turn on and emit light. So if we go back to how this was a second ago, oops. You'll see that this is... Oh, Unity, I did save you. There we go. So now you can see that while this is actually brightening up things in front of it, because it's not actually emitting light, it's not brightening by very much. Even if we add lots and lots of these in a row, it won't really brighten things very much at all. Now, what we can do here is we just set it to emission. Now, when we've got the emission in play, it will always emit that minimum level of light. So in the case of holograms, often you might want to have them emitting light. You might want to have them partially emitting light, partially not. And to do that, what you could do is you could use half of half. So what I can do is I can take this color value here. I can times it by 0.5, and that means it's half, and now I'm going to times the emission by 0.5, and now it's 50% natural lighting, 50% emitting lighting. That's one sort of potential option here. Now, this is not very interesting as far as hologram shaders go. From a hologram perspective, there's a few things we want to do. First up, we want to make this shader probably have some scan lines attached to it. We probably want to animate it a little bit. All those sorts of things. So now this is where we get into the sort of the nitty-gritty of what we can do with shaders. So we've got the very basics there, and I'm just going to emit this one back into almost full lighting. So I might set it to 90% from emission and 10% comes from actual reflections. Now, to do this, we've got a couple of options. The first option is we could do it basically from over time. So what I might want to do is bring in one of these Unity super variables. Now, again, I'm going to send you to the Unity reference docs a few times, because if you look up Unity built-in variables for shaders, built-in shader variables, you'll see a nice big chart, which will show you all these properties and things that are declared for you. Now, one of the interesting ones is time, and that's one we can use here to make things interesting. The other thing to look up is the CG function reference. So for shading languages, we use a language called CG, which is written by NVIDIA, and the advantage of CG is that it compiles to every platform. So it can compile to OpenGL, it can compile to DirectX. Unity do a bunch of stuff on top of it to actually take it to even more platforms. But these functions that are built in, if you search for CG function reference, these are all built-in math functions and things that you can use. So in this case, what we might want to do is, to start with, we're going to make the shader wobble in and out a little bit based on the time. So I'm going to use two functions here. The first one is saturate. And saturate basically is the effectively clamping it between 0 and 1, so you don't get negative values, you don't get positive values. Sometimes in a shader you might want to use negative values, so you want to make a shader that actually darkens the environment behind it. That can be done using these. It can also be done using the blend modes, but in this case we just want to use the saturate to clamp it to a normal range. Now the next thing we're going to do is we're actually going to multiply it by what's called sin time. That's a sine wave time, and we're going to use the .x property. It actually defines a bunch, but sin time.x, as spelt that way, will show you something. Now you're not going to see this animate straight away. While you have seen that it's changed, it's not really doing anything. What we can do is we can click here and click animated materials, and now you'll see that over time, maybe not very quickly, 1, 2, 3, I think it's over 20 seconds by default for the X. There we go. There we go. Now it's animating brightness up and down a little bit. Not very impressive, but you can see that it is actually animating rather slowly. Now the different properties on here, the X, the Y, the Z, whatever, those move a bit faster. So I'm just going to set this to Z, and this should go in and out quite a bit more regularly. Still a bit slow though. There we go. So you can see that's coming in. Now that's not particularly interesting from a perspective of how we want this this shader to look, but it sort of is the starting point of doing an animated shader. So the next thing we might want to do on this particular shader is to maybe have it influenced by the position on the shader. So what we could do is we can start with float3 world pos. Now we declare this in the input structure. Now we've actually got access in this variable here to the actual position in world. So what in the scene. So what we can do is we can actually do sin time. We can do frac, which is the fractional part of a variable. So it's the sort of allows us to do a sort of ping pong effect here. And we're going to times that by, we're going to add that to, in fact, add it to the in.worldpos.y. And now we've got something interesting. So this is a quick animated shader that's going to go back and forward. Now you notice it will go back and forward, and that's because the sine wave will go up and down repeatedly. If we want to just do a natural progression here, what we can do is we can actually change that from sin time to just time. And that's just going to be an ever-increasing number. So, we've got the start of a hologram. It's kind of there. We might want to change the direction. To do that, we just times it by -1. So we go times -1. We'll just put that in brackets for safety. You don't have to use as many brackets as I do, it's just paranoia. Okay. So, that's moving. Now, if we want to control the speed, we could change that 1 to maybe a 5. So now it's going to go really fast. Probably not very interesting though. Let's leave it at 1. Okay. So we've got the basics there, and in fact I may even I may change the scale of those stripes because that's being generated by the input coordinates. What we'll do is we'll just change that by 0.2. That means the stripes will get about 5 times bigger. So here we go. So the basics of something interesting happening here. Now the next thing we're going to maybe play with is vertex shaders. So what we can actually do is we can begin to modify some of these shaders. Let's make the hologram awful. It's going to wobble around a bit. What we can do is we can declare a function. Now I'm just going to cut and paste again from Unity's own manual for vertex shaders. Unity 3D vertex. I'm just going to grab the surface shader, vertex shader. So I'm just going to go vertex. Okay, here we go. So basically the template of this one. I'm just going to cut and paste this one in. You guys can do exactly the same thing. So here I'm just going to paste it. And I'm going to set vertex vert, and that means that we're now using my custom vertex shader instead of the Unity one that's built in. So what we're going to do is we're going to grab the vertex position and we're going to modify it. We're going to add a little bit to it based on the time variables. So what we're going to do is we're going to go float3 time.x. We'll do the sin time here. 0 sin time.z. Actually, we'll do x again. So what that'll do is it'll add a sine wave value to the position of the object on the x and z axis. So let's have a look how that looks in world. Oops. I'll save it. So whenever you save, Unity will actually recompile. So I don't think that actually had much of an impact at all. It's a bit odd. Did we actually compile? No, I'm just going to quickly test this. Sorry. Yep, so it is impacting. Maybe it just needs to be increased on the scale. So what we'll do is we'll just scale that by 50. Okay, so now, it's just slow, that's why. It's the same thing as before. We want to play with the fractional function just to make that a bit more interesting. So what I'll do is I'll just declare a variable here, which will be our modifier amount. Time.z, and we'll set that to times 5. So we'll set that to the modifier amount. And now we can get something a bit more interesting to come in there. So now our hologram is spazzing out a little bit, but that's okay. We can reduce that amount. So let's set that down to 5. So now you can see that it's doing something. Now that might be a little bit too fast, so let's set that down to 2. There's a bit of playing around here, and we can actually make some shaders, some sliders on the sidebar here if we want to actually change this. So what I can do is I can hit here. I'm just going to add a new slider, and this is going to be called wobble speed, and we'll set that to a range of 0 to 10, and the default will be 1. Now I'm just going to declare this one as a float, so let's go float, and it's going to be called wobble. Now, I don't know why it keeps playing around with my formatting, but there we go. And so I'm just going to put this one in here as wobble speed, and now I can use that in my vertex shader. So you can see here when I select this material, I've now got a new wobble speed slider. So in fact, I'll just select the shader, the material itself, and I've got wobble speed, so I can go, so it goes wobbling quite a bit, wobbling quite slow. And this way you can actually make things that your artists, if you're working with different people, can easily modify and adapt their shaders to do different things. So in this case, this is not quite ready. So this is wobbling quite a bit, but again, I think it'll look better when we actually make it affected by the world position. So we can use that here. Now the position here is going to be a little bit different. We use the vertex position. It's not got the same input structure. It's got something called app data full, which if you, again, Google will give you the list of properties of what's actually on app data full. There's a full layout here of what's actually available. So in this case, we've got position, normal, texture coordinates, tangents, color, that kind of thing, which covers the what's actually available in here. Anyway, so we'll just grab the vertex position here. So what I'm going to do is I'm going to add, on top of this, I'm going to add the vertex position plus v.vertex.y for the y coordinate vertex. And now we can see that this is beginning to go somewhere. It's looking a bit worse for wear, but if you saw that in world, you would presume that it's just a broken hologram. Now, this is interesting, but it's not really looking great. So there's a few things we can do to make this look better. First thing to do is actually look at adding a screen space overlay here. So what we're going to do is we're going to use an extra texture we make, and that extra texture is going to cover sort of some scanline effects. So I'm just going to grab it in Photoshop. I'm just going to make a really quick scanline texture. And to do that, it's going to be very, very, very simple. Whoops, grab that, and I'll just use a really hard brush. This is not going to be the world's best scanline texture, but it will do. It'll probably look a bit wonky. If you want to make an actual proper one, feel free. just do those last ones. There we go. So at least somewhat normal. Okay, and that probably needs to be scaled a little bit just to make sure that it's even. Okay. So what I'm going to do is I'm going to grab my folder, which is in Unity, and where did I put my found stuff? Masterclass. There we go. Here, I'll just drop it in here. You don't need. Doesn't matter where your textures go. Just as long as you're able to find them. Okay, and I'll save this out as a G, and we'll call this scanline. So now we've got a scanline texture. So the next thing we're going to do is we're going to add a new material slot for this guy. And now there's a few ways we could present this on screen. I'm going to show you both of them quickly. So I'm just going to add this new material quickly. This new texture slot. So I'm going to call it scan text. Let's get this, and we'll just add the sampler for it. Now, when you're reading textures, you probably want to be doing that out of the surface shader rather than out of the vertex shader, just as a general rule. You can do lookups in the vertex shader, you can do them in both, but we'll do it here because it'll look better. Vertex shaders are only run once per vertex, and the data is then interpolated between the vertexes when it comes down to the surface shader, if that makes any sense to anyone. So I'll just grab scan text. Now, what we're going to do here is we're actually going to multiply the emission amount by the scanline textures. The first thing we're going to do is we're going to import the texture so we can actually read it. So we'll go scan, and this is going to be scan text. Now the coordinates we're going to use here is we're not going to actually use UV coordinates for this one. We're just going to make our own. So we're going to use float2, which is means we've got an X and a Y coordinate because that's what we need for reading textures. And we're going to grab in.worldPos, well, for the X coordinate we'll just use 0 because it doesn't really matter, maybe 0.5 just to get in the middle of the texture. And then we'll use the input Y coordinate from the world coordinates to how this actually gets rendered. So we'll go in.worldPos.y, and now we're just going to multiply the emission by the scan. So just go times scan.rgb. Now that probably hasn't done enough here. Oh, right, the default has been for white because it's blank, but we'll just put that in. And now we've got something a bit more interesting. You can see here, because we're doing the blend modes, it's actually coming in partially transparent over there. So that's the sort of the basics of getting that scanline effect on here. It's a little bit wobbly, but we're making some progress. Now, if we're going to grab the player char, it's got a main camera. I'm just going to pull in the post zone we got before, because our post zones, if you remember from before, everything over a certain value, which is by default 1.0, will begin to bloom. So in this case, we've got our shader now. It's a little bit wonky, but let's make this bloom. So to do that, we just need to make the emission greater than 1. So I'm going to grab all these values, and I'm going to times it by 2. With a bit of luck, we might do 20. Let's just see, these values might be a bit dark. Do not have bloom on this camera. Apparently not. 1 second, we'll just make sure this is set right. Ah, bloom is off. That's why. There we go. That's better. That's what I was looking for. A little bit too strong at 200, but let's just try 2. So that's not really bright enough. 4, 3. Let's try 5. Just keep going until we get something we like. Okay. So this is sort of doing something. I'm actually going to set the albedo back down to 0, just so we've got only things that are emission. And where's my 0.9? I'll set it to 1.9. Okay, so we've got the very basics here. Now you notice the fog might be a little bit screwy with this, and this is because this texture is actually now no longer writing to the depth buffer properly, and that's because we've got the alpha test modes and things on. There is some ways of getting that to behave, but that's something we'll have to discuss later. So this is a starting point. Now the next thing we might want to consider doing is actually making the hologram that the edge is brighter than the center of it, and we can do that using a system called Fresnel or rim lighting. There's a great little cut and paste from the Unity surface shader example, so I'm just going to grab that one to begin with, and then we can cut and paste it. So you can see here, this is the example that's got it in here. So this one just uses two variables called rim color and rim power, and we can literally just paste these in here. There's not a lot of work that needs to go into this. So we'll just grab those rim power and rim color. I'll just grab those from here to here. I'll just put those in there. And finally, the rim, we'll just grab that one. Now, this is going to be need some slight adaptation here on this emission line, just to integrate it with our existing emission. So we'll just grab that, and we'll grab that. Okay. So now, this is a bit too bright, but we can play with this one. Oh, and also this had a custom value in the in direction, which I didn't implement, so I'll just grab that one as well. So let's input, we need the view position as well. Okay, so now when we look at our tree shader, we've got a rim control, so we can actually set how much it goes like this. Now what we might want to consider is the opposite, so it actually gets brighter on the center rather than the middle. To do that, we just invert the values. So go rim, we'll set that to 1, instead of where it's 1.0 minus, we'll just set that to 0. And now we've got the inverse, where we can actually control this. So, something interesting to read. Now what we might do is we might make this a bit brighter than the default, so I'll just go 1.0 and I'll set that to plus 1.0. And that way the rim lighting will always make it brighter instead of making it darker. So now this is looking a bit glitzy, but that's fine. We can mess with that one. We've got a rim color, so we'll set that to, oh, we're not actually using that value that we could use. If we don't add it, instead we add, don't multiply, instead we add rim color times that. We now will get control over this. So in this case, this is now got a red rim on the edge, but it's still very bright, so we'll just pull that one down. So, now we have got our holographic tree shader, and I think this is actually looking pretty kind of cool. So, something you might want to play with is actually making our avatars look like this. So this is cool, but we can make this look shiny. So the first thing we're going to do is we're just going to make our tree. I'm going to push it over there. We've got our shader. We have a system in here called the environment zone. Now this is a new feature that we've added recently, which basically lets us replace shaders selectively within an environment when it comes to players and instanced objects. So I'll just grab our player character is right here. So I'm just going to create a new cube. The only thing we need on here is the collider. We don't actually need the anything else on here. It's just for simplicity, I'm using a cube, so I'll just go there. Okay, I'm just going to make this a little bit bigger so we can actually walk into it. Okay, so when you are inside this box, we will make it so you can replace the player's shader with this shader that we've just built. So we're going to use shader environment zone, sorry. So we use environment zone, and under the character replacement shader, we just pick the one we wrote, so it's a Savannah shader. Now, the other thing we need to do is just set the box collider as a trigger. So it'll use any collider, whether it's a mesh collider or a capsule or whatever, just as long as its trigger is set. So, we have our player right here who's currently standing out of the box, and we have it ready to go. So we'll just hit play. And in a second, Unity will cook up. So this is just in our offline preview mode. Oh, and I guess that box, we'll get rid of the mesh on it, just so it doesn't look there. So we have our basics. So now when I walk in here, whoop, so this has got a bit funky, not quite how I anticipated, but that's because of the vertex modification. It's a little bit strong. So what I might do is I just pull this down in the shader. Where's our vertex modification? I'll just set that to 0.5 instead of a little bit much. I might set that to 0, in fact. Maybe not the the best use. This shader obviously has a few issues with it, but the neat thing is you can actually replace what players are looking like. I have a nifty shader which I'm going to use though, just as a demo. And I'm just going to pull this out of my folder. One of the Unity Japan developers, a guy named Kajiro Takahashi, has built a set of shaders which he releases on GitHub. This one is called Retro 3D, and it basically implements the affine rendering that's used on things like the Nintendo 64. So we're actually going to make our player look like it's part of an N64. So I'm just going to grab the shader file here. I'm just going to pull it into my Masterclass folder. Okay, it's called Retro 3 Unlit. So I'll just take my thing, I'll just hide the mesh renderer and swap this to Retro 3D Unlit. Now this is an unlit shader, so it won't apply lighting, but if we just go in here, okay, so where are we? Here we go. So this is now rendering the character as it would on a sort of an N64 style renderer, with quite cheap texture lookups and a bit of a broken rendering on characters. Looks better with low resolution models than it does with high resolution models, but nonetheless sort of showcases what you can do. So if you want to build something that looks like an N64 level, you could actually use shader replacement and things to achieve those kinds of effects. Now, shaders are incredibly powerful. You can grab tons of them off the Unity Asset Store. The way we work with space means that, generally speaking, 99% of shaders that are on the Asset Store do work with space. Even some of the more complex packs have been known to work. Some of the really complex ones, like the Relief Terrain pack, Lux, and a few others, need a bit of help from us in order to get going, but theoretically we can use all of those, and they can give you all sorts of various additional properties and modifications and things that can go onto your shader. So that is covering the very, very, very basics of shader design and development, which hopefully is useful. I don't have a ton of time left on my clock for other things, but hopefully those two bits and pieces are useful starting points. We might pick this up next week and just sort of carry through on some of the other things that I really want to cover. In the meantime, there was one topic that I really wanted to cover quickly as part of our development, as showcases, and that's animation. This is something that you guys probably may or may not be aware that's actually in Unity, but I think is worth covering, and that is the ability to animate anything to do anything. So we're going to start with that one, and this one I think we'll pick up on a future talk as well. But for now, what we're going to do is we're just going to do a very, very simple quick tutorial on animating things, and then we can sort of modify it a bit later. So the first thing we'll do here is we'll just make this tree bounce back and forward, just as a simple example. We'll make it shrink, and we'll change some texture, some shader properties as well. So to animate something, all you need to do is select it, go Window, and then there's Animator. Oh, sorry, Animation, not Animator. Animation. So it's Control-6 there, just like this one, and then you can create a new animation clip. So I'll just save this one as tree animation. Now, when we do this, we actually create a timeline. The timeline's measured in seconds, so the default is very tiny. So we'll just make this a 5-second animation. So we'll go from 0 to 5 there. So what we can do here is when we've got record pressed, so press record, now everything we do to the object will actually be recorded and added to the timeline. So what we can do is we can move this around, and you can see it actually added a data point onto there. So I will add a slight change and then just change it back. So I'll set the position to 1. The position is back to 0, and that way it's actually added a keyframe for the mesh position. Now, 5 seconds time, what we might want to do is make this one move. So now, when we hit play on the animations, you'll see that the tree is now actually moving to that position over time. Very basic, but quite simple. Now, the potential for the animator is actually quite a lot more. We can actually start playing with this stuff. So this rim power, or actually let's do the rim color, we can actually make this pulse to a different color. So I'm just going to save that color here, set it back. Okay, and now at 2 seconds, I'm going to have the rim color change to pink. And then at 4 seconds, we'll change it to something else, yellow. There we go. And then at 5 seconds, I'll just finish off with something else. There we go. And now, when we do the play on this one, you'll see that it'll actually sort of run through these things. Now, this is just some very, very basic examples of doing animations. You've got a lot more power. Anything on the inspector pretty much can be animated. Even the sort of the tick boxes and things like that will be picked up by the animation controller, so you can do things like toggle off shadows, things like that. Now, to make this animation more useful, what we might do is we'll just stop the playback, and that'll reset the timeline back to 0. We've got an animator on here. Now, this animator is going to run in a loop perpetually, and the reason for that is when we look at the animation controller, when you double click on it, you'll see this tree animation's there, and it's set to tree animation. Finally, when you get to that one, you'll see that it's looped. What if we wanted this not to happen until the player actually gets into a certain range? What we can do is we can very quickly, we'll add a new state. This will be our default state. This works as a state machine system, and again, I'm probably brushing over a lot of topics that are a bit more complicated. I will happily go into animators in a bit more detail in a future week. We'll just set this as a default state. We'll make a transition to this one, and we'll just add a trigger, and this will be a trigger that happens when we want in order to start the animation process. We'll go start will be its name, and we'll just set this transition to only happen when start has happened. So I'll just added it twice by mistake. There we go. So now we've got the default will be the tree, and when we hit play on here, this tree won't move. Because it won't be in the right state. It'll just be sitting permanently in that empty state we added. So, yeah, so here we go. Nothing special happening, just sitting there. What we can do, though, is we can make perhaps this clickable. What I'll do is I'll make it when you click on it, it starts animating. So I'm just going to add a clickable activator. Now this uses our event system, so I'm just going to add an event. I'm going to drag the object with the animator on it in here. I'm just going to select animator, and then finally there should be a set trigger. Set trigger, there we go. Our trigger is called start, so we'll just put start in there. And now, when we watch this, just give it a second to hop in. Now that's clickable, and when we press it, now you may notice it's not moving, and the reason is it's static. This is something to get you to remember, is that anything set batching static will actually become static part of the scene. So we'll just untick that one, and now it'll actually move instead of not. So now we go. You click it, and it goes. Now it's just going to loop in a loop like that. Now we can actually do things like ping pong loops and other kinds of loops from here. That's something we'll come back to in a future tutorial, but hopefully this has been a sort of good introduction to some of the more fancy features that we can do in Unity, and next week we'll dig into the stuff that I mentioned at the start that we didn't get to finish today. Thank you guys for showing up, and I will be doing my in-world office hours in a moment to talk about some of the new things that we've got coming down the pipeline and what's been finished. Thank you very much.